Hi folks, now we're going to be talking about the Earth's atmosphere. The point here is basically the Earth's atmosphere is pretty thin, and as you can see by this picture I got off the internet from Beijing on a clear day and a smoggy day, we breathe this stuff. As you know, the atmosphere is mostly nitrogen and oxygen, but you may not know how the atmosphere gets created. Okay, so the atmosphere or planetary atmospheres gain gas in a couple of in a few different ways. From volcanoes, carbon dioxide, nitrogen, sulfur, things like that get produced. They get heated up, as you know, and so a gaseous discharge will occur. One can see that on the Earth by going through clouds of volcanic exhaust, if you will, and find out what's actually in that exhaust. The other thing that you've seen is undoubtedly evaporation. And then the other thing you may not be aware of is the effect of solar radiation or other types of radiation hitting their surface and thereby relieving the surface of some gaseous content. For example, as you know, the Earth is composed of a lot of silicon dioxide, and if you have a very energetic X-ray hitting silicon dioxide, you can break apart the silicon from the oxygen and create oxygen gas from that. So that is perhaps one way of doing that. You can lose gas by actually condensation back onto the surface, chemical reactions on the surface. But you can also lose gas by if you have large impacts, say, for example, meteorites or something. You're going to, expel a lot of gas, but also material. But on top of that, if you've got an atmosphere, you can hit the top portions of the atmosphere with energetic X-rays or other types of electromagnetic radiation. They can cause the molecules to break apart. So, for example, water can be broken apart into its constituent elements of hydrogen and oxygen. The oxygen would be retained on Earth because it's more massive than the hydrogen, and the hydrogen would escape. On the other hand, you can hit these gases and get them more energetic, and then the atmosphere loses those gases as well. Okay, so our initial atmosphere was just the materials that we would see in the solar nebula, basically hydrogen and helium. But if you go to the NAAP website, as indicated here, you can run a simulation showing you that we're going to lose this material pretty readily. The equations that are used here are shown here for you. In our case, the mass of the planet is equal to the mass of the Earth, and the size, we can set these things equal to each other. So, on the surface of the Earth, the escape velocity is about 11 kilometers per second. If you run the calculation for the gas, and you use hydrogen as an example, then you're going to get something like 2 or 3 kilometers per second. Remember, the molecular mass for hydrogen gas is quite small, and the temperature is about, say, 300 degrees. In this particular case, we do have the velocity of the gas is about 3 kilometers per second, and then we have the escape velocity being 11. So this inequality is basically telling us that hydrogen gas would escape. Remember, what we have here is about 2 or 3. Here we have 11. So 11 divided by 6 is about, is a little bit less than 2. Here we have the velocity of the gas being about 2 or 3. So we would see that hydrogen gas would escape over the period of time. Here's a more detailed picture of what's going to happen. This is a curve that we have seen before in terms of the energy associated with a black body radiator, and basically they're very related in that regard. So, basically physics is an equal, we apply everything Once we solve something, we apply it to every single process. It turns out that it works. Okay, so what ends up happening is we're going to, basically tells us that we're going to lose the lighter molecules. So the heavier ones will stay put. So where do the nitrogen and the carbon dioxide come from? Well, they come from volcanoes, as we talked about before. And where did the oxygen come from? Well, that comes from life. Oxygen is very, very reactive, and it is actually one of the telltale signs if we have life on other planets. Oxygen is very reactive, and it will combine with anything. The only way you can create oxygen in an atmosphere is you have an overabundance of it, or you're creating so much that the elements on the planet do not absorb it. For example, if you leave an iron nail outside, it will rust. It will turn into a pile of red dust. We talked about that before. So oxygen is being absorbed out of the atmosphere and is combining with the iron in the metal, creating a compound, iron oxide. So oxygen just in the atmosphere of its own accord is a strange sort of thing. All right. It was first thought that, what I was saying was generally the case, but we found that oxygen just by itself is very common. It is very rare. Hydrogen by itself and carbon monoxide is much more common. Atmospheric pressure, as you know, as we get higher in the atmosphere, the pressure gets less. And the heating also will increase the pressure. So, those of you that are familiar with the Santa Ana conditions we have in the LA area, we have a wind that is coming from the desert, a high pressure. So the high pressure pushes the air into the LA basin. The desert regions are about 6,000 feet in elevation, and the LA basin is about 100 to 1,000. So the air increases in pressure, increases in temperature, going hand in hand. And so that's why when we have these types of weather phenomena, it gets very hot in the LA basin, and it gets hotter the closer you get to the ocean. And very strange that way, but entirely explainable. All right, where does the atmosphere end? Well, as we saw before, the atmosphere is about 10 kilometers thick, but there are pieces of it that go out pretty far. 100 kilometers, so, it decreases as an exponential factor, decreases so that, there's less and less of it as it goes out, but if you will, it could extend forever. But it's sort of ridiculous to think of it extending forever. So 10 kilometers of what we're talking about. 60 kilometers has an effect on satellites, and so periodically satellites have to be controlled. You have to have a rocket burn in order to gain altitude, because the atmosphere will cause the satellite to run out of gas, if you will, and to crash if you don't accommodate for that effect. We're basically talking about drag in this regard. Okay, the atmosphere has some, there are some pieces of it that have some strange behavior. There are 4 layers to the atmosphere, and we'll talk about that as we're going along here. There are 4 different effects that we see with the atmosphere, especially in terms of light's effect upon it. As you can see here, we're talking about absorption and scattering, those things you see on a daily basis. Why is the sky blue? Why are the sunrises and sunsets red? And it's basically scattering and absorption. As the sun gets lower and closer to the horizon, the red light goes through, the blue light gets absorbed and scattered. When the sun is overhead, we see blue sky everywhere. That's entirely from the scattering. Just ask yourself the following question. If I see blue light away from the sun, where ultimately did that light come from? Your answer should be that that light is coming from the sun. But your eye sees it not from the sun, but some angular distance away. I mean, your eye sees it coming from a totally different direction than from the sun. But ultimately, that blue light has come from the sun. Now, there are other effects that light can have, and we saw that with the previous lectures. We can basically destroy atoms, and we can destroy molecules. So that's what we're talking about, dissociation and ionization. So let's take a look at the structure of the atmosphere. In the very beginning, or the very lowest region, we have the troposphere, and the temperature decreases as a function of height. If we go to the next layer, we are characterized by temperature increasing to a peak value and then decreasing. So what we're talking about is this, where I'm starting to decrease and come back over, that's where the layer stops, and the layer stops here as well, doing the same thing. We're decreasing and then we're increasing. So this region is the stratosphere, and the temperature increases, and right here we have ultraviolet rays being absorbed by the oxygen molecules and thereby creating ozone, and there is a natural connection between ozone and the oxygen atmosphere, O2, ozone being O3. So the ultraviolet rays are creating ozone and then breaking them apart, and that process continues. Then the next layer, then the next layer is the thermosphere, and basically from here on out the temperature just increases. This is the last little bit, if you will, of the atmosphere. And then we do have a region called the exosphere, which just goes out into space. I mean, it's sort of unclear what's going on, why we have another one out there. Okay, the effects of the atmospheres are manifold. The primary one I want you to think about, or these effects I want you to consider in regards to other planets. Venus having much more atmosphere than the Earth, and Mars having much less atmosphere than the Earth. And those have been the planets that we have considered in the past as perhaps having life on them. Certainly we're still anticipating that life was on Mars for a while, but Hollywood has given us movies that, like Mars Attacks and the Amazon women of Venus and that sort of thing. So in popular culture, we sort of have a thought that maybe there were, intelligent life on those planets, and perhaps they would come by and attack us or something. But atmospheres have a critical part to play in the environment of a planet. If you have more atmosphere, you have less effect of day versus night. You can create liquid water if there is enough atmospheric pressure. And basically you can have an interaction also with the solar wind to create such things that are on my bucket list to go and see. The Aurora Borealis, for example. That's closer than the Australis. All right. The next step is to consider climate. And what we want to first talk about is circulation cells. Around the equator of the Earth, the solar radiation is going to be more intense on average than up at the poles. Up at the poles, the light rays are going to graze and heat up this region a lot less than the direct radiation that we would normally see along the equator. Now, granted, the Earth's got a tilt of 23.5 degrees, but what I'm talking about is on average. So, on average, the tropics are much warmer than the poles. I think you'd grant me that. Now, the Earth, if the Earth was not rotation, did not have any rotation like a rotisserie when you're cooking chicken, then what would you expect to have happen other than this? Around the tropics, the air would become heated, it would become less dense, and it would rise. And then in the poles, it would become colder, become more dense, and fall. So that would create a natural circulation, falling in the north, and it would travel down to the south, to the equator, warm up, and then rise up again. And in the southern hemisphere, we would have the opposite occur. In the South Pole, the air would fall, and it would then move along the surface of the Earth and rise around the equator. So that's what we would expect, and that's without rotation. Okay, but there is an effect associated with rotation, and that's called the Coriolis effect. And that's most easily seen in the following video. So let's take a look at these kind people from MIT and what they have for us. So they don't have much sound associated with this, but as you can see, they're throwing the ball back and forth. Now the idea is that one of these folks is throwing the ball straight ahead. And as you can see, they cannot catch it because the ball is not along their axis of travel. But here, you can see that when they throw the ball, that the ball goes straight. The ball goes straight, but they are not. That's why they are not able to catch it. And naturally, you could throw it in such a way as you could lead the catcher, and just like a quarterback leads his receiver. But that is not what we want to try to show here. We want to show the basic idea of the Coriolis effect. So he's throwing it straight, but when we're in the frame of reference of this rotating frame, we see that the ball curves. He throws it straight, and it misses us. Throws it straight, and he misses it, although that time you can saw he led it a little bit. Simple-minded physics. I love it. And as a scientist, you have to do it in the other direction just to show that it has the same effect. Okay, so what is the Coriolis effect on the Earth? Well, hurricanes or cyclones have this characteristic shape. They go around clockwise in the south and counterclockwise in the north. So take a look at the hurricanes that are up here, and then the hurricanes that are down there. That's one example. And what ends up happening for the circulation cells is that we have 3 being created. So we have, where before we had 1, now we got 3. And in these particular locations, these were what were called the doldrums. So shipping, when people were running around with sails, you didn't want to be in this location because you didn't have the trade winds going on. Now, when we go to other planets that have much faster rotations, we'll see that they have more circulation cells. That is, stay tuned for Jupiter and Saturn. All right, so planetary temperatures are dependent upon these parameters here. So a lot of things can affect planetary temperatures. The idea is, you might say, first of all, the distance from the sun. Very sort of standard thing to think about. But the amount of atmosphere also has a role to play. You can think of the atmosphere as a blanket. So at some point in time, the amount of radiation that you absorb from the sun and that which escapes from the planet we'll certainly come to some sort of equilibrium. All right, but when we talk about climate change, think about the short-term effect of us putting more carbon dioxide in there. That's effectively changing the thickness of the blanket that you're putting on for the nighttime. So all of a sudden you've doubled the thickness of the blanket. What's going to happen? You're going to warm up until at some point you come to some equilibrium. Okay, well, that's the problem that we've got now. The equilibrium, we don't know what it's going to, we haven't measured what it's going to be, but we can predict what it will happen. Okay, other things that can affect the atmosphere is albedo, and that's basically the color of the planet. So if you have snowball Earth, then a lot of the radiation that's going to hit the Earth is going to be reflected off of the snow. And if you've ever traveled in the snow, you know that you got to wear sunglasses and put suntan lotion in your nostrils. Otherwise, you're going to get you're going to get sunburned in your nose, which is kind of, I've had that happen, and that's really disconcerting. It really hurts. Okay, naturally, if we have a differing amount of tilt, we can have a differing type of planetary temperature going on. Think about Uranus in this regard. Uranus has a tilt of almost 90 degrees, so sometimes its North Pole is directed completely or directed directly, towards the sun. In that particular case, the North Pole warms up and the South Pole is completely frozen. Of course, the southern hemisphere is completely frozen. And we can think of rotation rate as well. You turn that rotisserie chicken going really, 90 miles an hour, the whole thing is going to cook up pretty evenly. Okay, so greenhouse effect. The idea here is visible light penetrates the atmosphere a lot more readily than infrared radiation. And the infrared radiation spends a lot more time in the atmosphere. As you can see by the picture, it's bouncing around a lot more. You can get that effect, and this is where the name comes from, by what happens in your car during a relatively cool day. In fact, you roll up all the windows, the car is going to get pretty warm. If you're in a summertime situation, that car can be 120, 130 degrees, and that's why you don't want to leave children in your car or animals, because you'll kill them because it gets so hot. But the idea is that is the same as before. Okay, if you put more stuff in the atmosphere, then you're going to create a thicker blanket. Now, to say that the greenhouse gases or greenhouse theory doesn't work, let me remind you from this chart that if we did not have a greenhouse gas, if we didn't have greenhouse gases, then we would not be in a temperature regime where we would flourish. Simply put, we already have a greenhouse effect. The effect is pretty significant. Here we are with Earth. The effect of the greenhouse is to increase the temperature of Earth by 30 degrees Celsius. Remember, that's of the order of about 60 degrees Fahrenheit. If we had no greenhouse gases, we'd be really, really cold, minus 16 degrees C. That's like, minus 32 degrees Fahrenheit. And remember, water freezes at 32, not minus 32. Now, as you can see here, Venus has got a really significant greenhouse effect, and basically it's always at that temperature. Mercury has very little greenhouse effect. There's like no atmosphere on there, and you can see it has a very wide-ranging temperature, going from essentially, the maximum coldness you can have to the maximum temperature you would see so close to the sun. And you can see that there is a slight effect on Mars. Okay. The other thing you can see is that the nighttime temperature for the Moon and for Mercury is the same, because when that happens, you're looking into deep space. Reflectivity has an effect, as I talked about before. Basically, if you're on snow, you have a lot of reflection off of the snow. If you're not there to absorb the energy and get a sunburn, then that light will go into the atmosphere and basically out. Albedo can be affected by such things as the color of the surface. It can be effective by clouds in the upper atmosphere. Those things are white, as you can see from pictures of the sun or pictures of the planet from the moon. And so the Earth has an albedo about 30 to 35%, as it says, by cloud cover. Okay, temperature and tilt. And so if you have more of a tilt, naturally you're going to have more station, you're going to have to wait longer until the rotisserie effect takes place. And the same thing applies to rotation. The more rotation you've got, the more even the temperature over the planet. Okay, so this is the last bit I have. Kind of a cute thing. I want to impress upon you the effect of climate change upon us. The planet doesn't care what we do. It's always going to be there. Okay, talk to you next.